The following content is for entertainment and educational purposes only. It does not constitute means for diagnosis, healthcare advice, nor treatment. Make use of a qualified healthcare professional for such purposes.
Good afternoon, everyone. My name is Dr. Charlene Ortiz, and today we are going to continue with our understanding as to how we are going to interpret data, that presentation of that data. Now, previously, we covered aspects of central tendency, right? So we talked about mean, the mode, median, and then we started talking a little bit more about variability. So for instance, how is it that data is going to vary from one place to another, for example, in the respects of the mean or within the data itself. So today we are going to continue in discussing methods that we have in order to measure variability. So let's get started. All right, so if you remember from our previous lecture, when we are referring to variability, variability is simply a measure. It's simply a measure that is trying to understand that spread, right? So if we go to our previous illustration from earlier lectures, which will indeed be linked in the description below, the measures of central tendency let us know that we have, right, distribution. For example, this one specifically is normally distributed. So when we're thinking about variability, what we're thinking about is how spread out is that information in respect to the rest of the measurements that we have. So that is our understanding of variability. So in continuing, and how is it that we can measure variability? We have another method in addition to the previous ones that we talked in our previous lecture. So I highly encourage you to visit that video as well. Let's talk about sample variance. Sample variance. Now, in regards to sample variance, what we're trying to do in regards to sample variance, as you know, it's also a measure of variability. And what we're going to do is we're trying to compute that average. We're trying to compute that average. And that average is going to be squared, right? So notice that we're going to have that average squared. Now, the intent is to identify that distance of those samples in respect to that mean. So, as I mentioned earlier, what we're trying to do is find out the distance, right? What distance do we have when it comes to that data? How far does it fall from this mean, right? From this measurement. So any questions about the definition of a sample variance? Now, something that we would need is generally, we will focus on the degrees of freedom. And if you recall, N signifies the amount of observations. So for example, if I survey a classroom, right, and there are 100 students in my class, that is my N. The N is the amount of observations, the amount of data, the amount of data points, data sets. There's many synonyms, but they mean the same thing. N is simply the amount of data sets of participants. Now, in order to calculate the degrees of freedom, if we go back to our slides, the only thing we would need to do is reference that N. So for example, 100 students participated in my study, -1. And that is going to give us the degrees of freedom. And again, N is that sample size. Now, the next thing that I want to note is that we will also, for the equation of sample variance, right? So we define sample variance squared and we define degrees of freedom. Let's talk about the sum of squares, right? This is simply the sum of all deviations, of these deviations from the mean, right? So it's the sum of all the deviations from that mean. And when we are talking about the specific equation, right? Because I'm going to erase all this. In order to calculate the sum of squares, we would need to first, in order to calculate the variance, I will need to calculate the sum of squares, I should say. So notice that in order to do so, I have the sum of a specific data set, right? A specific data set minus my m squared. Later, I can populate this unknown, right? I like to call these unknowns, whenever we are referring to an aspect of an equation that we don't know, I like to refer to them as unknowns. So if you hear me saying that term, I'm talking about something, well, we just don't know that yet, but we will calculate it. So every time you hear me say unknown, that's what that means, right? I'm referring to whatever aspect we don't know as of yet. Any questions about how to read and understand the sample variance? Any questions? Good deal. Good deal. Let's go to our next slide. Now, there are some aspects that are advantageous when we are thinking about a sample variance. Well, firstly, one of the good things that we can gather is a clear interpretation. And why is it that that sample variance can give me an interpretation? That is because the larger that sample variance, right? So for instance, if I have my bell curve, right? Beautiful, I know, I'm getting better at this. Watch, by the end of the semester, it's gonna be perfect. It's gonna be like the bell from Pavlov's dog, you know? It's exactly what it's gonna look like, I promise. I'm working on it. So, in keeping again with this bell, not Pavlov's, think about the larger that sample variance, right? The further away that data is deviating from that mean, right? So we can show that there is indeed some sort of variability. And I'll give you an example. So let's think about, for instance, let's think about variability, right? I'm trying to see the differences between these 100 students, and all of these students are going to go to therapy, right? And we're implementing this new therapy, right? And let's assume that this is the average amount of, let's think about disorder. Let's see. Individual is bipolar with psychotic features. All right, so this is the average bipolar with psychotic features, which would be, most of you don't have, right? So I would expect this is 0, right? But let's assume that 100 of those students, they were selected because they have bipolar disorder with psychotic features. So this would be the average. I would expect these people without treatment to fall in the mean, right? Now, what I'm trying to do is, once I start seeing variability, right? So for example, I start noticing that people start reporting less psychosis, their symptoms, for example, they're doing better, or their scores in whichever assessment I'm using to determine their symptoms of psychosis because of bipolar disorder. Notice that those numbers are going to start deviating, right? They're going to start moving away from my mean, right? So I can observe that variance. I can observe that variability. Now, the issue, however, that we have, if we go back to our slides, the issue that we have, oddly enough, is that this data is reported squared, right? If you remember from our equation, right? If I clear my slide, notice that this sample variance is squared. The issue with that, or limitation, stems from most of the data that we come across is not squared, right? So for example, if I am talking about a score of psychosis, and I tried to compare it with the rest of the population, notice that the score, if I were to show you that assessment, generally it's not squared, right? Generally it would be a more basic number so it can be understood correctly. But there's a fix, right? There is a fix to address the fact that this variability is percentage squared, right? And that is through standard deviation. Any questions about the advantages and disadvantages of sample variance? Good deal. Now, because of the disadvantage, we have to use standard deviation because that would be a more clear method to present that information. Let's go back to our slides. Now, standard deviation. What is standard deviation? In a very basic sense, we're talking about those average scores, right? What are the average scores that are moving, right? That are moving and deviating themselves from that mean. Generally, we are going to represent a standard deviation. It's going to be represented as SD. I've also seen it represented as S. It's pretty rare. It kind of threw me off when I did see it, but it's most of the time it is illustrated as SD. And all it is we're going to grab our sample variance. All we're doing with standard deviation is calculating the root. That is all we're doing in order to calculate our standard deviation. So if we go back, if I erase all of my annotations, notice a standard deviation is simply going to calculate the root of our sample variance. That is all we are doing. Now, interestingly, something that I would need to mention, right? I'm going to make this a little bit larger so it's a little bit easy to understand. I'm going to make it as large as I can because it's a little bit difficult to understand when it's so small. But nonetheless, Dr. Schauer is in the recipe, right? So when we are thinking about standard deviation, for those of you who like target practice, right? For those of you who like target practice, think about how many notches, right? When you're adjusting your sights for target practice, think about how many notches you have to move from that mean, right? So for instance, right, when you have that type of instrument, think about when you're trying to adjust sights, it's going to be one notch from the average, or maybe two notches from the average, and so on and so forth. Standard deviation to me refers to those little notches, right? How far are we from the left or the right, right? Negative or positive from the mean. So let's show you an illustration of such. Now, in regards to standard deviation, notice that again, we have a bell of normal distribution. If we have a bell that's normally distributed, you will see that the mean, mode, and median are going to fall right down the middle. Right, so this is your M, right? This is your mean, this is your average. Also represented by an X tilde. Now, a standard deviation, like I mentioned, is those little notches, right? That fall, whether to the left. So here's 1, here's 2, here's 3, and then here's 1, here's 2, here's 3. Notice that that is the distance, right? How much are we deviating from this mean? But this is actually very informative, right? As your slides mentioned. This is actually very important, and it's really informative because now, for example, if I grab any number, so for example, we have, say, in the illustration that I gave you, let's think about students who are bipolar and have psychotic features for their bipolar disorder. Let's say if we do that assessment, the average score for psychosis when it comes to bipolar disorder is a score of 20. Now, Previously, when we had the sample variance, that was not as informative. But with standard deviation, if I say, okay, let's say Billy, nobody here named Billy, fantastic. So let's say Billy had a score of 23. Notice that my first standard deviation were from 20 to 24. So that is telling me that Billy is still falling within one standard deviation, right? It's moving one standard deviation. He's still within the frame of normacy. Any questions so far? Any questions whatsoever? Good deal. Now again, it is informative because now when I start getting real examples, for example, Billy fell here and it was 23. And let's say that Rebecca had a 17. And then Kendrick scored, let's say, a 26. Notice that now my standard deviations are giving me a little bit of an understanding. Why is that? Because now I know how far these scores are falling from this mean right here, from the average. So basically, how average is Billy? How average is Rebecca? How average is Kendrick? Any questions about that? Good deal. Now, how do I know that both Rebecca and Billy are still falling within the norm, as I mentioned? That is because of the distribution, right? A distribution of a normal curve. Generally, as a rule of normally distributed data, we know that at least 68% of all of our data that is normally distributed is going to fall within one standard deviation, within one notch, if you will. So if I go back to our little illustration, notice that if I erase all this, and I like using colors for this one, notice that within one standard deviation, whether it be from the negative side or the positive side, 68% of all the data ever covered, all of this data in the middle is considered norm, is considered normal, if you will, because it's still falling within that center range. Now, if we go back to our previous slide, notice we're going to erase this here. So 68% falls within one standard deviation. Now, within two standard deviations, we're going to find that about 98% of all of that data will fall within two standard deviations, right? So notice within two standard deviations, we're going to see that about 95% of our data falls within those notches, right? Those steps, if you will. So again, if I try to illustrate two standard deviations towards the negative and two standard deviations toward the positive, notice that about, in this particular case, matter of fact, I have a better way to illustrate that. So notice that that information there, falling within two standard deviations, you'll see that about 95% of all this information is going to fall within two standard deviations. Lastly, we refer back to our empirical rule. Notice that about 99%, 99.7 of all of your data is going to fall within three standard deviations. Within three standard deviations. So if we refer back to -3 or +3 standard deviations, notice that in here, all of this data refers to about 99%, 99.7 of all that population, all of the sample that you just gathered. Now, theoretically, these two lines here that you're seeing here, these two lines extend to infinity. They just never touch. They just extend to infinity. Just never touch, right? So technically, you can still have information, say, for standard deviations, right? You could still have that information. But notice that will be an immense outlier, right? And an outlier, right? An outlier is a data point or data set that doesn't seem to behave like the other data points, right? So for example, if we have all of the data basically concentrating, floating, behaving around the mean, when we start seeing a data point that falls really far away, 3 standard, 4 standard deviations, when we start seeing data like that, notice that this data set, this data sample, the sample point is behaving, as I like to refer to it, not in accordance with that norm, right? It's not falling towards that center. Any questions about the standard deviation? Good deal. So if we go back to the example of Rebecca, Billy, and Kendrick, right? Let's think about their psychosis. So if I have Rebecca here, I think I gave her a 17, so let's do that. And then we have Billy here, and Billy has a 23. Would you say that these two people, do they fall within the realm of normacy? They're still within that expected range? Or do you think that they are not? Who can tell me they are not within that normal range? All right, so you guys believe that they're still within that realm? That is correct. They're still within that one standard deviation. And I would expect that most people are basic, right? Because you guys know, you guys are not basic. So you guys would be the whole over here. You know what I'm saying? Positive 4. You guys are special. Any questions about the standard deviation? Good deal. All right. Any questions from online, our virtual audience? All right. Okay. Good deal. So sometimes, as a little fun fact, sometimes you hear individuals who, I'll go back to that slide very quickly. So sometimes you'll hear information, some more of the controversial topics. So for instance, for those of you, my specialty is forensic psychology. So sometimes we hear about these controversial cases. For example, let's think about an individual who is going to be executed because they were found guilty, were convicted, were prosecuted and convicted for a serious crime, and they have a set date of execution. Well, actually, one of the things that has to be conducted is, you guys might have heard a lot about insanity pleas and things of that nature, right? The ability of an individual being able to understand the charges against him or her, the ability of an individual to, in some states, to understand the difference between right and wrong. In some states, the ability to understand whether or not that mental illness did indeed is directly related to the crime that caused the crime, if you will. But some of you might have not heard basically competency to be executed, right? Some people may be set to an execution, but they may not be found competent to be executed. And sometimes you'll hear individuals, well, let's do an intelligence assessment, right? And as you know, the average score for intelligence is 100, right? And sometimes people will say, well, he scored, let's say, an 89. All right, the individual scored an 89. Notice that with a standard deviation of 15, this individual will still be considered within the norm, right? Even though the average is 100, that person will still be considered within that 68%, right? Within that one standard deviation. And I know that's a little controversial topic, but it's a really good illustration of seeing, okay, If the average is 100 and this gentleman or this lady scored an 89, some people would say, well, this person is clearly not competent to be executed, right? The person won't even know why they're being executed. Well, in that sense, statistically speaking, I'll make that very clear, statistically speaking, the person is still falling within one standard deviation, so he matches about 68% of the population. That's a really good example on how we utilize standard deviations in the real world, the very serious aspects of society. So any questions about that? Fantastic, good deal. All right, let's go back to our slides. Good deal. Yeah, you do see that quite often. The pleas and I mean, they're doing their job, right? To defend the individuals. That's how our justice system works. So I can understand it. Now, for those of you who have SPSS available, whether it be at home or at a library, notice that in this specific case, this is a data set that we could utilize, right? That we could utilize in order to start calculating, first of all, measures of central tendencies, so mode, median, and the mean, and also measures of variability. So for example, sample variance and our standard deviation. Going to leave this up on the screen for a few seconds so that you're able to pause it. And if you have the opportunity to calculate these at home or at a library at your convenience, this is a good data set to utilize later if you're interested in calculating these by yourself. Now, for those of you who are here in class, we would have the opportunity a little bit later on in the semester to actually show you how exactly these are calculated with software, with SPSS. Going to leave this screen also. Going to leave this screen up here. So let me go ahead and share this screen. So these will be the steps that you would have to conduct in order to calculate central tendency and variability. I'm going to leave it up here for just a couple seconds so that you have the chance to follow along at home. Pause it and follow along at your convenience. Now, let's talk a little bit more about how is it that we are able to represent, right? How are we able to represent this data? Well, so far, you've been exposed to a lot of numbers, right? So far, you've seen a lot of numerical values, mostly letters, quite frankly, right? Who had to do that, right? Starting adding letters to numbers, make it complicated for the rest of the world. So we do have means to illustrate this information in a fashion that it can be better understood, better illustrated. Not only that, it can also allow us to see the behavior of the data, right? So something really interesting about graphing, right? You're not going to graph something just, for giggles. Because if you graph something for giggles, first of all, you're wasting the audience's time, but also that data may be irrelevant, right? It might be irrelevant. So whenever you graph something, you want to make sure that you can exploit this data, that you can understand the behavior of the data in a visual sense, because it might be a little difficult to understand the behavior of data with numbers, but later when we graph information, sometimes it's easier to understand the behavior of the data. Now, let's talk about different types of graphs, So if we go back to our slides, let's start first with graphing means, right? Graphing means. There are different types of graphs, and in this specific case, let's talk about bar graphs. Now, when it comes to bar graphs, the first thing that we would need to focus on is that bar graphs are used to illustrate nominal or ordinal data, right? It's the first thing that we need to remember, because this is one of the few methods that we have to illustrate data that otherwise wouldn't necessarily be considered numeric if you will. Because if you remember nominal and ordinal data, one of the things that it allows us to do is give numeric values to things or categories that are generally not considered numeric. So for example, I can create a bar chart of my favorite food, or let's change this to, let's say, mental illness, right? Very straightforward. And the diagnosis of a mental illness, if it's related to the time that you are able to attend to a task, right? But notice that mental illness is not necessarily, right? If we go back to our slides, notice that mental illness is not necessarily a numeric value, right? It's a category. Mental illnesses are a category, right? For example, we have the category of mood disorders. We have categories of trauma and stressor related disorders, right? So notice that we don't have a numeric value, right, for a mental illness. What we have is a category. So because of that, we can start graphing this information through bars, right? So for example, do you have a mental illness or not? Yes or no are categories, right? They're not numerical. So we can say, for example, that individuals who have a mental illness have spent more time trying to tend for the task. It's more difficult, more tedious, say when compared with persons who reported a no, right? And of course, this is a fictitious example for illustrative purposes only. So if you compare both, notice that in this fictitious example, we have two categories, right? We have two categories right here, the yes or no with the category of mental illness, right? So we do use it for nominal or ordinal data. Now, conversely, right? Conversely, we also have an line graph. Well, before I go there, when we are talking about the means represented with bars, what I am referring to, right, if I erase all my data, this would be the average of all of the data, of all the persons that answered yes, and this is the average of all the persons that said no. For example, that average came about to be a 12 for persons who said that they had a mental illness, and then the average for the persons who said no came about to be like a 9, it seems, or a 10. But notice that Peter's data set is here, and Jessica's sample is in here. And let's say Roseanne is in this data set, right? So Roseanne is here and Peter is here. So notice that each individual score was used to calculate, right? So we have, let's see, what's a common name? Joanne, so we've got Joanne over here, right? So notice that we have all that spread, all that variability, if you will, but remember that these are categories, right? So we're only going to have that average, right? So that's what that refers to. Right? We're only going to have the average of all those little data sets. So Peter scored a 2 and Joanne scored a 5. We're going to have all of those different categories for each. So that's what that refers to. Now, let's go back to our other example, right? We can also use a line graph. And more specifically, we're moving away from that nominal and ordinal, right? We're moving away from that nominal and ordinal. And now what we're doing is we're trying to tap into that integral and ratio scale, right? Now, interestingly, one of the things that we're going to do is, if you recall from previous lectures or previous classes, you'll recall our x-axis and our y-axis in an illustration. I probably mentioned it here, but I'll mention it again because I love torturing you. I love educating you, right? So I promise you that's an arrow pointing that way. I promise. Promise that's what that is. So you'll know that the x-axis falls horizontally, and you'll remember that a vertical axis is always our y. And one way that I never forgot how to remember is why would you jump off a cliff? So I always remembered, oh, it's the vertical one because why would you jump off a cliff? So that made an awful sense to me. And I'm passing that along to the young minds of Alabama, right? So remember that the groups are going to be listed in that x-axis, okay? So remember, when you are illustrating your data, it's generally represented in the category. The categories here, right, are always going to fall within that x-axis, okay? Now, what we're going to do in this instance is that we're going to connect, right? We're going to connect all of those means. We're going to connect them through dots, right? It provides a little interesting observation of how that data is behaving. So let's look at an example. Let's look at an example. So let's erase all of these data points here. So notice that in this regard, let's change this to, let's talk about, let's do psychosis. I like that. All about psychosis today, aren't I? All about psychosis, right? So, or another way to illustrate, there we go, with the side. So, say for example, these numbers here, I need you to recall, right? It's like if we were going to give yes a value of 1 and no value of 2. Remember, these numbers are artificial, they are fictitious because we're not really counting, right? We're not really counting. These are simply artificial, right? You can't say that yes is less than no, right? That wouldn't make sense. So let's assume in this specific sample that this category is going to be psychosis, right? So the category of psychosis, and say, for example, in regards to the data that it's matching the DSM. There we go. So psychosis as illustrated by DSM. And again, this is a fictitious, fake, mock example, okay? So say the individuals scored, say, 2% of all the symptoms as illustrated by the DSM. And let's say this is 5% of all the symptoms, and this is 10 or more. And then for the case of our example, we're going to say, okay, persons who are have scored 10%, these are the people we're going to look into later on. So here we're going to have that mean, right? So for example, we have the categories, and then here we can change, instead of amount consumed, we can say amount of breaks, right? Amount of psychotic breaks of these persons, right? So psychotic break, psychotic meltdown, whatever term you like to use. So notice that the persons who reported that consistency with this category, notice that they reported more issues in the past 5 years with psychotic breaks. So we can start seeing a behavior, right? We start connecting the data, the means, and what that tells me is that the greater, right? Seems like there is a behavior here, that the more matching they have with symptoms, then the more likely they were to have a psychotic break. Should this have been a correlation, right? So, any questions about both types of illustrations? Any questions so far? Good deal. Yes, ma'am.
Is the center value the mean?
So let's think about this. When we are thinking about the mean, this is going to be in comparison to each one, right? So each one is going to have like their own mean. So if we say, so the question was, for those of you watching at home, is this value the mean, right? So if I understand you correctly, basically thinking that that value is this value. Is that your question, basically? Okay. So the question is, does that value represent the mean? Well, technically, each one of these is a mean, right? Each one of these is the mean. For example, the amount of people who met 2% of the diagnostic criteria, 5% of the diagnostic criteria, and 10%. So technically, they're all means, just like in a previous example. So this is the mean for people who said yes, and this is the mean for people who said no.
Okay.
Does that make sense? Good deal. Good deal. Any more questions? Good deal. Fantastic. Now, when we have correlations, right? When we have correlations, we want to conduct a scatter plot. And why is it that we want to do a scatter plot? A scatter plot is a fantastic way to see the behavior of data that should or should not be related to one another. So for instance, in the previous fictitious example that I gave you, say the more the person matches diagnostic criteria for psychosis, the more psychotic episodes they've had in the last 5 years, right? So that is an illustration of a correlation. The good thing about a scatter plot is that it's going to show me those points within, if we go back to our slides, it's going to show me that display, right, of points of X and Y, right? So for example, if I have my X and my Y, whenever I do a scatter plot, it will want to say, okay, Peter met 5% of the criteria and he falls within this range. And then we'll see an example, right, of a relationship later on. Now, if you remember the scatter plot or a correlation, a scatter plot is going to allow me to summarize all of my data, right? Because say, we're doing a pretty easy example, right? Say 20 people, but what if it's 100? What if it's 1,000? So I want to see an easier way to understand my data. And a scatter plot would be a fantastic way and feature to do so. Now, if you recall from our previous example, right, you'll remember that in previous lectures, we talked about positive and negative relationships. As a matter of fact, I'm going to link down in the description a very, very, very detailed description of what correlations are. What are they used for? How to calculate them. So that video is going to be in the description below. If you want a really in-depth understanding of what correlations are. But in a very basic sense, correlational and correlations in statistics, what we refer to as the relationship between X and Y. Is this factor related in any way to this factor? Now, we have multiple types of relationships, but we're going to talk about right now 2 relationships. The first one is a positive relationship. Has anybody heard that term before? Is that something that you're familiar with? What can you tell me about a positive relationship? Fantastic. So, Dr. What's your first name? Stephanie. So Dr. Stephanie over here says that a positive relationship is when one of the values goes up, the next value will go up. That is correct. That is a positive relationship. Now, also, if a value goes down, the other value goes down. That is also a positive relationship. Because positive and negative doesn't mean the sense of more or less. It's simply, right? So we're not adding or subtracting. What we mean by a positive relationship is that both data sets are going to go the same direction, whether they both go down or they both go up, right? So we need to remember that that's what a positive relationship is. Conversely, a negative relationship is that when one data set goes up, the other data point goes down. And vice versa, right? If a data set goes down, the other data set goes up. So notice that in this case, when we are talking about a negative relationship, what we are referring to is that the data sets are going in opposite directions, right? Both going in opposite directions. I'm going to walk like an Egyptian doing that, right? That's a reference. That's a reference. If you have not, Google going to walk like an Egyptian. It's a song. Yes, it's an older song. That's a reference. Hashtag getting older. All right. So there's one, you guys can't see it on screen, but there's one sentence, just look at me. Why did I get myself into this? It's like, why am I here? Stuck little old me, huh? I'm sorry?
Just make people old.
Oh no, we're seasoned.
Yeah.
That's a better term. I'll take that one. Not old, I'm seasoned. But we're not here for seasoning in KFC. We're here for positive correlation. So that's what we're doing. So notice that in this particular example, here we have a body image satisfaction, right? So we're going to pretend that we have a sample of individuals and we gave them a questionnaire. And in this questionnaire, the lower, right? So we're ranging from 0 to 10. The lower the score, right? The more these people were exercising, or excuse me, the less they were exercising. So if we have, for example, the person had a score of 2 with body satisfaction, notice that the score would be a 20. But say, for example, a person who reported more body satisfaction, right? They were working out more hours, right? More minutes a week, right? So notice that the relationship is positive. The higher one number, the higher the next number, right? So notice that this will be considered a positive relationship because as body image went up, so did the minutes per week that this person was working out. Conversely, let's talk about other relationships. So in this case, we have the grades of a person. So we took a sample of students and the quizzes were for the semester. They had multiple quizzes and the scores range from 0 to 10, as illustrated in our x-axis. And this is the amount of times the person did not show up to class, right? So 0 times compared to having 10 absences in a semester. So if you notice, the more absences, right? So 9 absences, the lower the score, right? So this person who was out and about, just hanging out, going to the beach, right? Having fun. This person, because they were absent more times, they had a lower score versus people who were only absent one time, right? They were only absent one time, but their score in class was a 90, right? They had a score of 9. So notice that the greater one variable is, the lesser the other variable would be. So this will be considered a negative relationship, and this one's a positive relationship because they both went the same direction. Whereas in this one here, as one went up, the other factor went down. Therefore, this is considered a negative relationship. So any questions about positive and negative relationships as illustrated by a scatter plot? Now, again, when we are looking at a scatter plot, it tells us a lot of information. Is it a positive relationship? Is it a negative relationship? Is there no relationship for that matter? Actually, a no relationship looks like this, right? So we would have basically a horizontal line and our data is just going to be all over the place, right? So let me illustrate this for people at home. Let's do that one more time. So this was positive, this was negative, and generally, when we have a sample, a relationship where there was, in fact, no relationship, generally it looks like this. So we have a regression line, and then the data is all over the place, right? There's no real pattern. There's no real behavior. Whereas in a positive relationship, you see that the data sets are behaving a certain way. They're generally moving towards a positive, right? Moving towards a positive relationship. And here at the bottom with our negative, notice that the data sets are behaving a certain way. We can see that they're falling close to my little regression line. But here, we just have data all over the place. None of them is actually following a general behavior. They're not falling close to that regression line. And we'll actually talk about regression later on in other aspects. But again, if you want more detailed information of what is a correlation, please click on the link below for the video about correlations. And I go in depth and very much in detail as to what that is and how to calculate a regression. So any questions about positive, negative, or no relationships for that matter in regards to a scatter plot? Good deal. Fantastic. Good deal. Now let's go back to our slides. to now, one of the things that we would need to discuss is we talked about central tendencies, we talked about variability, we talked about how to show that data, right? But we have talked previously in other lectures about internal consistency, internal consistency. Now, what we mean by internal consistency, what we're trying to find out is we're trying to determine, right? We're trying to determine to the extent in which multiple items are actually, right, are actually related, right? They're actually related. What does that mean in the Queen's English, right? What does that mean? Well, say, for example, that you and I are developing this new assessment. Right? It might even be a test here for class. Right? Let's keep it interesting. So we're going to keep talking about the individuals with psychosis. And think about, okay, I want to develop a tool to measure this psychosis. So we have a first item, right? I sometimes see things that other people can't see. And our second item can be sometimes I feel the room gets cold and I can't explain it. Right? And the third item is I like pups. Right? So notice, right, and this is a really clear, observed example. But what we're going to do with measures of internal consistency, we're trying to find out that reliability, that they actually remain consistent, that they're actually verifying that these items are indeed related to each other should they be measuring the same thing. I would expect that items that are not measuring the same thing will not be related to one another. Whereas items that I consider that are in fact measuring the same thing, they should have a high level of consistency, right? Because they're measuring the same thing. Any questions about what internal consistency is? All right. Now, if we go back to our slides, notice that we have a potential way to measure this consistency, right? How consistent are these items with one another, right? That they're actually measuring and are consistent with one another. Well, we're going to use Chromebox Alpha, right? Chromebox Alpha. Now, Cronbach Alpha, of course, is a measure of internal consistency. But what is it exactly? Cronbach Alpha is basically trying to estimate that average, right? It's trying to estimate that average correlation between all possible ways that measurement, that assessment that you are creating, that those items can be split in half, right? So for example, we have all these little items. So let's go back to that example that I gave you about psychosis. So my first item was, I see things that other people can't see sometimes. So that's my first item, seeing things that other people can't see. The room gets cold, right? That an explanation. And here we have our little dogs. The happy dog. That is a TikTok reference. So I am cool with the kids. Look at that. Fantastic. I'm hip. I know. So notice that what Chromebox Alpha is going to do is going to try to split in half all of that data and see how much, right? How much of that consistency remains in all the possible halves, right? So my first half of data, my second half of data. And what I'm trying to do is find out that consistency, right? If my items are indeed measuring, right, what they are intended to measure, first of all, and secondly, if they are consistent with one another, I would expect that the scores that you would get here, right, are similar to the scores that you would get here. there shouldn't be that big of a difference if they're actually consistent, right? The Chromebox Alpha is trying to find out that consistency, right? I would expect that if I were to split all of that data across. Any questions so far of what a Chromebox Alpha is set out to do? Any questions? Good deal. Now, remember, N is that amount of observations, right? The amount of participants. In this case, it will be the number of items, right? So if I had all these items, right? And I have 10, or hopefully you don't only have, all the way down to 10. Hopefully you wouldn't have only 10 items to address psychosis. I feel like it would take a little, maybe not, maybe it doesn't take that many. Now, let's look at the equation, right? Let's look at the formula for Cronbach Alpha. Now, we're going to have, of course, our amount of items. So for in this case, we have 10 items. And the 10 items minus 1. Now, notice that one of the first things that we would have to discover, right, is our sigma, right? You're thinking, well, where do I get that? Well, we actually just talked about it not so long ago, right? So let's go a little bit back to our previous illustration. And when we are referring to sigma, we're generally referring to that standard deviation, right? That standard deviation. And we will find the standard deviation for each item, right? So say for example, the standard deviation for IQ is 15. Okay, perfect. And say the standard deviation for the psychosis that I was talking about earlier, say we're going to pretend that it's going to be 20, right? So for Rebecca and Bill, for their psychosis, the average for the score is going to be 20. So we're looking into that variability, right? So the variability that we had earlier. So what is the variance across all of the items? And then we're going to have the sum of that standard deviation, but now we are referring to our y-axis. We're referring to our y-axis. So this translates to this little section here. So notice that the first part, I'm trying to notice the variance for all of my items. So for example, the standard deviation in our previous example, I think it was a 4, if I'm not mistaken. So you have 2 points. So one standard deviation between the mean and the negative is 16 and 20, so 4. Right? So notice that in this case, we will have, okay, across all items is 4. And then we're going to do the same thing for the y-axis, although this time we're going to calculate for each item, right? So we would have to go back, right? If we had our data set, right? For example, we had all of the points. So let's think about the score for Rebecca, the score for Billy, the score for Kendrick, right? So I will have to go to each individual data set, right? So this data set, so on and so forth. And I will have to calculate them individually. But don't fret, because SPSS does that for you. But I do show you all of the illustration of Cronbach Alpha, so it makes sense. Okay. Any questions about Cronbach Alpha? I know that it can get a little confusing, but hopefully when seeing the illustration, okay, well, N is the number of items. And then I'm trying to see what is the variance, right? What is that standard deviation, if you will, across all of the items? So it appears like we look back to our little example. And of course, this is for illustrative purposes. Notice that what is that distance? What is the variance? Well, the variance was 4, right? 20 to 24, right? So that's 4 right here. So notice that it remains consistent, right? So for one standard deviation, it doesn't change, right? It's consistent. So 20 to 24, 24 to 28, 28 to 32. So notice that standard deviation will remain the same number. Right? That's why you see it illustrated here as plus or minus. right? Because it moves either direction, negative or positive. All right. Any questions about Cronbach Alpha? Any questions about what that equation, or I should say that formula means? Good deal. Fantastic. Now, whenever we get that value, right? Whenever we get the value of Cronbach Alpha, just like with correlations, because remember, we could argue that Cronbach Alpha, it's also a correlation. So if you remember from previous lectures, and I'll illustrate them again here today. Notice that when we are talking about a correlation as well as Cronbach Alpha, notice that the results are always going to range between 0 and 1. Right? So 0 to 1, meaning that the greater, the closer your value, the Cronbach Alpha, right? Cronbach Alpha is to 1, the more consistency, the more related these items are to each other, right? These halves are related to each other. So in regards to this type of correlation, the higher the value, right? The closer we are to this number 1 right here, the stronger the correlation to those items, right? The stronger the relationship between those items. So in the example that I gave you, think about, I see things other people can't see. That's item number 1. The room gets really cold and I can't explain it, right? Or other people can explain it. That'd be a good one. So notice that in this specific case, let's assume that in the purpose, in keeping with our little fictitious example of this assessment that you and I are developing together, notice that we have a different rule of thumb. So, of course, the higher the value, I should say, the more preferred. But if we have, say, for example, we didn't get that perfect 1, right? And normally we won't. I'll tell you that because, as you know, behavior is much more complex. And therefore, because it is much more complex than just one characteristic, generally we're never going to find, or it's really difficult to find a perfect relationship, right? A perfect 1, right? That's really difficult. Or negative 1, right? So don't forget, we also have that perfect, right, relationship. Don't forget about that. Now, if we get a value closer to the 70, that's generally acceptable, right? We will accept that in literature, but we're aiming for an 80, right? We're aiming to get a score, a relationship between these items. We are trying to get to an 80, right? So that is our preferred value. Now, the ones for relationships in general, they're a little different, right? They're not like this one. Generally, poor relationship, very mild is 0.3. And for other, kind of like moderate, we have a 5. Anything greater than 7, you're looking for. But for Cronbach Alpha, not for R, not Pearson's R. But for Cronbach Alpha, we would take this general rule of thumb. Basically, we are shooting for a 0.80 accuracy, if you will. Any questions on how to interpret that Cronbach Alpha? Right, we're shooting for a 0.80, but we generally accept 0.70. So now let's talk about Cohen's K or Cohen's T. So in this specific case, right, we talked about previously about internal consistency, right? But now we're going to talk a little bit more about Interrater, right? Interrater reliability, right? And what is Interrater reliability? When we're thinking about Interrater reliability, think about, say, we're developing this assessment for psychosis, right? We're developing this assessment for psychosis, and then we have a panel, right? We have a panel of individuals that are known in their field, right? That are experts in psychosis. And we're going to have these individuals quite literally at face face value, look at my assessment, right? Would sit down, look at my assessment and say, does this look like it's measuring psychosis? Does this look like it's measuring depression, right? So the example that I gave you earlier, I see things other people don't see. The room temperature gets cold and I can't explain it. And then I said, I like puppies. All of you went, that makes no sense. That's Interrater right there. You as a judge are listening and reading, for example, this item is saying, that doesn't sound like it has anything to do with psychosis. Bro, we know, I mean, it might. Maybe we do a Chromebox Alpha and we find out, oh, wow, that actually predicted something, right? There's actually a correlation. But at face value, in our Interrater reliability, it doesn't seem like that's actually what it's doing. So if we go back to our slides, that Cohen's K is the measurement, right? For Interrater reliability. And it's pretty simple, right? It's pretty simple, it's pretty straightforward. So we have our, for example, our percent of agreement and our percent of expected error. Right, so it's pretty straightforward, right? Percentage of agreement minus the percentage of expected error. Now, how is it that we come across that expected error, right? Well, we need to take into account the probability that there is a chance of error, right? There is a probability that we say, well, clearly liking puppies is not psychotic. It doesn't represent psychosis, but there is an amount of error that it could potentially be an item, right? That it could be an item that predicts psychosis. Therefore, I have to include that amount of error because for all we know, it is, right? For all we know, it could be a measurement of psychosis. Now, we're going to conduct an example. We will be conducting an example at some point when it comes to our lab. For those of you who are watching at home, I'm going to leave this up for a couple of seconds so that you can pause the video and be able to conduct these steps in order to calculate your Cronbachs or your Cohens. I'm going to leave this up for a few seconds. And by the same token, we have our K, we have our Kappa. And I'm also going to leave this up for a couple seconds so that you have the ability to conduct these at home or at your own convenience. And for those of you who are here, we will have the opportunity to see these in our lab. All right. Now, we talked about how we are representing data. We talked about how we present data, but notice that we can engage in deception. We can engage in misleading or distorting the data in order to satisfy a particular agenda or purpose. Why is this unethical? You may say, well, it harms nobody, right? If I tweak a number here and there. The problem is that your audience, right? That your audience is going to consider that there are differences, right? That there are instances. That there are instances that your data does represent and prove that variability, that we're actually observing aspects, right? Aspects that we truly consider that that presentation of data that you just gave me is legitimate. Why is that unethical? Well, think about that you're presenting your research, and your research is going to be used on actual people. So if you find out this new assessment, this new instrument about psychosis, and it has Dr. So-and-so, and you start publishing it, although I would think that that would be taught beforehand. But notice that people are going to inform their decisions based on your data, right? a practitioner in their office, in the hot seat with the client, they're going to use the information that you developed for real life purposes. Because remember, psychology in general terms is considered a public science. What does that mean? It means that it's supposed to serve individuals, right? Psychology is considered a public science. There's disadvantages to that, of course, because it's so public that then people start making their own ideas, come up with like, oh, it must be borderline. It's like, I don't think you know what you're talking about, right? But notice that because it is consumed, the fact that you are presenting this data in a non-ethical fashion could lead to significant consequences to others. There are some issues, for example, whenever we are trying to present our graphs, we may leave a label behind. That's a problem, because if I don't label my graph, I can make it out to be whatever I want. Right? I can say, oh, that wasn't categories of mental illness, that was, then you make it sound to whatever you wanted it to sound like. Generally, another issue is that we tend to represent a graph that doesn't begin in 0. So for example, you saw me earlier, right, drawing my little graph. I was always putting a little 0 here. I don't know if you noticed, but I usually do that because that is the correct way to show data. Right? Generally, this intercept here is represented as a 0. Be immensely careful, right? Pay close attention of how exactly are you illustrating this data? Is it misleading, right? And we see that very frequently. We see that very frequently in public venues, right? They would say, oh, there's a relationship between my product and how long you live, right? And they show you this graph, and it turns out there is a relationship between you using my product and how long you live. But what's the significance? Did it actually matter? Well, if you use my product, you're going to live longer. And it turns out you're only going to live a day longer. Was that an actual significant, right? You're only going to live an hour longer. Right? So was it actually significant? Right? So we're lying through deception, right? We're lying through omission. So you have to be very careful about the data that you present. Now, when we are talking about statistic, one of the issues that we may have whenever we are presenting our data is that you can just omit data altogether. So in the example that I just gave you, you say, oh, there is a relationship. If you use my product, you're going to live longer. But you left out that there was no statistically significance. It wasn't really that important. It didn't extend your life that much longer. You can also commit the error of trying to exaggerate those differences. So for instance, you can say, these people using my product, these people using my treatment method, these people using my medication are going to be doing great, right? They're going to have a great quality of life, but it turns out that when we did our research, they reported, say, a mild benefit from the medication. Now, generally, we want to report data that occurs together. We want to report it together, right? We don't want to be misleading. Right? We don't want to be misleading. So generally, we do want to report data that stays together so we don't give the wrong impression. Now, something immensely interesting is also your role as a consumer, not just as a researcher. Be really mindful, have a lot of critical thinking. Use these types of lectures to say, I don't want to be deceived. Let me go back to that data. Let me look at that methods and that results section and say, I don't think this matches the other. I don't think this different matches a great significance. So are there any questions about the ethical side of data presentation? All right, fantastic. And I'll see you Thursday.